So now that we have an understanding about functions, let's look at what we call optimization. Optimization is where you take a situation and you're trying to find your maximum or your minimum value. To do this, we first have to do a few things about the problems. Usually there's lots of words in the problem, so you need to read the problem very carefully, try to understand what the problem's asking you to do, and try to define any variables that you happen to have in the problem. To define those variables, it helps to draw a picture first. So it helps to get that picture down of what your situation is, label everything, and then including labeling everything, you can have some quantity that you want to maximize or minimize, that you want to optimize. Figure out what that quantity is. You can call it anything you want, but let's call it Q for the moment, just to have something to talk about. And you're going to let Q be that quantity you're going to be maximizing. Then you're going to write an equation for that Q, whatever that equation happens to be that is from the situation. If you have multiple variables, you want to first write Q in terms of one variable so that you don't have multiple variables in there that you want to try to maximize around. You're going to look to find the domain of that quantity. And then, or of all your functions that you have, all the variables you have in there. And then you're going to find your absolute max or min, especially if you're in a closed domain, you can do that. You can use the first or second derivative test to show what your max and min is. You can check your endpoints. And then you're going to write your answers in some kind of words. Because you started with words, you should end with words. So let's take some examples. Let's consider the following problem. This is a box with an open top is to be constructed from a square piece of cardboard 3 feet wide by cutting out a square from each of the 4 corners and bending up the sides. Find the largest volume that such a box can have. So we know from this last sentence that we want to find the largest volume. So largest means maximum. So we know from this that we're trying to maximize volume. So we're going to look to say we're going to maximize volume. So that's the quantity I'm going to work with. Let's call that V for volume. And again, a picture would be very helpful. I have a square. So let's go look at that square. Let's go draw a square. So here's my square. It's 3 feet wide. Because it's a square, it's also 3 feet long. And we're going to cut out squares from each one of the corners. So let's call that, we know that these are 3 feet long and wide, but we don't know how big the squares are. So that's a variable we don't know. We don't know what that is. If I don't know what it is, I give it a name. Let's give it H for some name. And so these are all H because they're squares. And since I just wrote down a letter, I should write what that letter is. And that is the length of the squares cut out. All right, so now let's see if we can find out a few more things about this. One of the things I know what I'm going to do is I'm going to cut these and I'm going to fold these sides up. So I'm going to get a side folded up, another side folded up, and all 4 sides folded up. It makes a box. The height of these, the length of these heights is H. That's what we call that. Those are H's there. And one of the things I notice is from, once I told it out, from here to here, this length here, the whole thing was 3, and I took out 2 H's. So this is 3 minus 2H. So this length of this side over here on the box is 3 minus 2H. Over here, same thing. This length here is also 3 minus 2H because we took out the 2 H's. So we have our variables figured out. We've got our picture drawn. Now let's see if we can figure out what we want to maximize. We want to maximize volume. This is a box. It has no lid, but it still can have a volume. And the volume of this box is the area of the base. Say the area of the base, because it's a square, is just each length times itself, which is a square of that, times the height. So it's 3 minus 2H quantity squared times your H. I notice this is only in terms of H. So this function is a function of just h, so I don't have to worry about getting myself out of having multiple variables. I only have one variable to work with. That's good. Well, technically two, because I also happen to have the volume, the v, that's another variable, but we only have one. Okay, so another thing to look at is what can h be? So let's try to find the domain of this. What might be useful here is let's go ahead and write this out. Let's go ahead and let's go ahead. I'm trying to get my path. My thing won't work. There we go. So let's multiply this out. So this will be 9 minus 3 times 2 is 6 times 2 is 12h plus 4h squared times h. Multiply through, we get 9h minus 12h squared plus 4h cubed. So far, so good. And then we can go ahead and we have that. We don't need to have those parentheses, so I didn't really need those. Let's also figure out what the domain is. Well, the smallest h could be, because h is my variable, the smallest h could be is 0. I wouldn't take that out, but the smallest it can be is 0. The biggest it can be is the whole side of 3 feet. It won't be that, but those are my domain I can work with. So now let's find the derivative, because we now want to maximize it. So we'll find the derivative. 9 times 24h plus 12h squared. Set that domain equal to 0. Let's see what we can factor. We can factor out a 3. That'll give me 3 minus 8h plus 4h squared equals 0. And let's keep factoring. I like to have my h squared term first, so we can just think about rewriting this. This will be 4h squared minus 8h plus 3 equals 0. So maybe that's 2h and 2h. And maybe let's do minus 1 and minus 3, because that'll give me minus 6, and minus 2 is minus 8. So I now can see that we have that, and now I can see that h can be 1/2, or h can be 3/2. So we've got two different values for critical points here. We need to figure out which one actually is where the maximum occurs. You can use the absolute max ideas, or we can use the first derivative rule. I'm going to use the first derivative rule in this case. So here's 1/2, here's 3/2. I'm looking at my factors of 3, 2h minus 1, 2h minus 3. When h is 3, it's always positive, so that one's not a problem. When h is, let's put the 1/2 up here and the 3/2 up here so we can read things a little better. When 2h minus 1 is 0 at 1/2, if we take a number less than it, like let's say 0, we're going to get a negative number. Take a number bigger than it, you're going to get a positive number. 2h minus 3 is 0 at 3/2. Take a number smaller than it, like 0, you're going to get a negative number. Take a number bigger than it, you're going to get a positive number. Negative times a negative times a positive is a positive. Negative times a positive is a negative. And all positives is positive. So we want maximum. So remember, the first derivative test tells us if we're positive to the left, negative to the right, we were increasing and then decreasing. So we have a maximum at 1/2. Then we're decreasing and increasing, so we have a minimum of 3/2. So I now know my max volume occurs at a height of 1/2 feet. So let's see what the volume actually would be, because I actually want to know what the volume was. What is the largest volume? So I now need to take my volume equation. I now know where the volume is maximum. I need to now find that volume, take that volume equation, my volume equation. And I don't remember it, so let's make sure we get it right. It was 9h minus 12h squared plus 4h cubed. 9h minus 12h squared plus 4h cubed. That's my volume. Let's find the volume at 1/2 where my maximum occurs. So that would be 9 times 1/2 minus 12 times 1/2 squared plus 4 times 1/2 cubed. And I get 1.532 is the, and that's cubic feet, is the volume of that box. So I can now say that my maximum volume is 1.532 cubic feet. Let's do another problem. This one says if a resistor of R ohms is connected across a battery of E volts with an internal resistance R, spelled that wrong, ohms, when the power in watts in the external resistor is equal to P is equal to E squared R over R plus little r squared. If E and little r are fixed, but big R varies, what is the maximum volume of the power? So this is the power. We want to find the maximum volume. The nice thing about this one is we don't have to find the formula. We already were given it. That doesn't always happen. So you'd have to do like we did on the first problem of finding that. But we do have the power here. We are then going to find the derivative of that power. So this is a quotient. So I'm going to use the quotient rule. Remember, E is constant, little r is constant, big R is what's my variable. So E squared is just a constant. So it's E squared times R. The derivative of E squared times R is just E squared because the derivative of R is 1. So the derivative of the top is R squared, E squared, times the bottom is big R plus little r squared, minus the top of E squared big R, times the derivative of the bottom. But the derivative of the bottom would be, it's a chain rule. So it's 2, bring the power down, times the inside to the first power. So big R plus little r to the first power, times the derivative of the inside. And the derivative of the inside is just 1, because the derivative of big R is just 1. All over the bottom squared. But the bottom was already squared, so it's now squared squared, so it's the 4th power. We're going to set this equal to 0 and find out where that is. We also need to look where when it's undefined, but I'm noticing that we've got R, big R plus little r to the 4th power. Big R plus little r will always give you a positive number, so you're never going to have 0 on the bottom. So we don't need to look at where we're undefined because you never will be undefined. So we're just looking at where this thing is equal to 0. That's going to equal 0 when the top, E squared times big R plus little r squared minus E squared times big R times 2 times big R plus little r equals 0. So let's see if we can do a little bit of factoring here. I'm noticing there's an E squared in both terms. I'm noticing the big R plus little r in both terms. I notice this the lowest power is the first power, so that's the one I'm going to take out. So we have all that. We're going to factor out a big E squared times big R plus little r quantity. When we pull out of the first one, we're just left with the big R plus little r. In the second quantity, the E squareds go, the big R stays, the 2 stays, the R, big R plus little r cancels. Or not cancels, but is factored out. Equals 0. So now that we have that, we can set each part equal to 0. Well, E squared is never 0, so you can just ignore that. You can divide it out if you wanted to. We have big R plus little r, so big R is equal to minus little r. This other one is minus big R plus little r equals 0. So big R equals little r. So those are our 2 values. Those are our 2 critical points. Using the first derivative test, we have a little negative r and capital R. This again is what r prime is, I'm sorry, what p prime is doing. Remember we had e squared, so that was one factor. We have, and I would put all the factors, even if you're like, well, I don't need that, it's just a constant, because it could be negative and it will change things. So always put all your factors. You have a big R plus little r, and you have a minus big R plus little r. This was 0. E squared is never 0, and it's always positive, so we have positive, positive, positive. You have big R plus little r. That was 0 at negative r. If your number is less than negative r, like negative 2r, negative 2r will give you a negative number. If you're bigger than negative r, like r, you're going to get a positive number. Negative r plus little r was 0 at just little r. If you're smaller than little r, you're going to get a negative, you're going to get a positive number, because you're going to have a small number from a bigger number. So you're going to have a positive number. And if you're bigger than negative r, you're going to be a negative number. So if you're bigger than little r, if you pick like negative 2r, you need to have negative 2r plus little r. That would give you a negative number. So we have positive, negative, positive, that's negative. Positive, positive, positive is positive. Negative, positive, positive is negative. Again, what we wanted to do is we wanted to find the maximum value. We wanted to find that maximum. We didn't write that down anywhere. It would have been good probably to do that. Again, negative means we came down. A negative driven, we're decreasing and then we're increasing. Then we're increasing and then we're decreasing. So we're increasing up to little r and then decreasing after. So the resistance of little r will produce a maximum power.